Hello, my name is Anisa Halimi. I'm a PhD student at Case Western Reserve University. This is a joint work with my supervisor, Erman Ayday. This talk is about efficient quantification of profile matching risk in online social networks using belief propagation. An online social network is a platform in which individuals share vast amount of information about themselves, such as their social and professional lives, hobbies, diseases, friends, and opinions. Via online social network, people also get in touch with other people that share similar interests or that they already know in real life. With the widespread availability of the internet, online social networks have been a part of our lives more than ever. Most individuals have multiple online social network profiles for different purposes. Furthermore, each online social network offers different services via different frameworks, letting individuals share different types of information. Also, in some online social networks, users reveal their real identities to find old friends, while in some other, users prefer to remain anonymous, especially in online social networks in which users share sensitive information about themselves, such as their health status. An online social network can be characterized by its graphical structure, the connection between the user, and the publicly available attributes shared by the user. Here, the privacy risk is the de-anonymization of the anonymous online social network profile of a user using their other online social network profile in which the user is identified. But why do we want to match user profiles? Users are the ones who decide what information to reveal about themselves, so information across different online social networks is usually incomplete and even sometimes inconsistent. Profile matching helps us to build complete profiles of individuals to provide better personalized advertisement. It enforces data consistency and simplified account maintenance. It raises the potential for new services such as better background checks, people search engines. From the other side, it also has serious privacy concerns. If an attacker is able to link an anonymous profile of a user to their real profile, they can obtain privacy-sensitive information and might use this information against individuals for discrimination or blackmailing. Since the number of users in online social networks is increasing, it is very important to find out at what extent profile matching is possible. For simplicity, let's describe the general threat model by considering two online social networks. The auxiliary online social network that includes the profiles of the individuals with their real identities, and the target online social network that includes anonymous profiles of individuals. In general, the attacker knows the identity of the individuals from the auxiliary online social network and is aiming to determine the real identities of the user in the target online social network by using the publicly available attributes, the graphical structure, or a combination of them. It is also generally assumed that there exists a one-to-one matching between users. In other words, a user in the auxiliary social network can have at most a matching user in the target online social network. In general, there are considered two different attacks, the target attack and the global attack. In the target attack, the attacker aims at finding the corresponding profile in the auxiliary online social network of the anonymous profile of a target individual in the target online social network. In the global attack, the attacker's goal is to de-anonymize the anonymous profiles of all individuals in the target online social network by using the information in the auxiliary online social network. Most previous works build different classifiers to determine whether two user profiles are matching or not. First, they train classifiers such as k-nearest neighbor, decision tree, random forest, support vector machine. Then, when a new user pair comes, the trained classifier returns the probability of this pair of being coupled or uncoupled. They use attributes such as username, location, gender, profile photo, or graph connectivity. The drawback of these methods is that they offer low precision. In our previous work, we showed that Hungarian algorithm provides significantly better precision and a comparable recall to the machine learning techniques. First, we computed the contribution of each attribute using logistic regression. Then, given some user profile in the auxiliary social network and in the target online social network, the general similarity between every user pair is computed by using the identified weights of the attributes and the individual attribute similarities. To obtain a one-to-one matching between the users in the auxiliary social network and the users in the target online social network that will also maximize the total similarity, we use Hungarian algorithm. However, assuming that there are n users in the auxiliary social network and n user in the target online social network, the running time of Hungarian algorithm is O(n) cubed, and it's not scalable for large data sets. This raises the need for efficient, accurate, and scalable algorithms for profile matching. So we propose a new framework. In general, our proposed framework consists of three main steps. In the first step, profiles and attributes of a set of users are obtained from both online social networks to construct the data set. For each user profile, we extract username, location, gender, free text, posts, connection, and so on. We assume that profiles are selected such that some profiles in the auxiliary social network and the target social network belong to the same individuals and some do not. We refer to the profiles that belong to the same individuals as coupled profile and to the profiles that belong to different individuals as uncoupled profiles. In the second step, once the attributes of the users are extracted from their profiles, we first categorize them to compute the similarity values of the attributes between different users. We categorize the attributes by using some known social media mining and analysis tool. For more details, please check the paper. In the third step, the tag type is determined and profiles to be matched are selected. Every profile in the auxiliary social network is paired with every profile in the target social network, and the similarity between them is computed. Inspired from the effective use of the message passing algorithms in information theory and reputation management, in this research for the first time we formulate profile matching as an inference problem that infers the coupled profile pairs and develop an algorithm that relies on belief propagation. Belief propagation algorithm is based on a message passing strategy for performing efficient inference using graphical models. In the next slides, we formalize our approach and present the different components that are needed to quantify the profile matching risk. Our goal is to obtain comparable precision recall and accuracy value as in the Hungarian algorithm with significantly better efficiency. We formulate the profile matching, in other words, determining if a profile pair is coupled or uncoupled, as computing the marginal probability distribution of each user pair given the similarity values between them. Since the number of users in online social networks is high, it is computationally infeasible to compute these probabilities. Thus, we represent user counts in online social networks as a factor graph. A factor graph is a bipartite graph containing two sets of nodes, variable nodes and factor nodes, and edges between these two sets. Here we show the factor graph representation of a toy example, which consists of 3 users from the auxiliary social networks and 2 users from the target social network. We form a factor graph by setting a variable node for each profile pair, shown as a rectangle. Thus, each variable node represents the marginal probability distribution of that profile pair being coupled. We use 2 types of factor nodes: auxiliary factor nodes, representing each user in the auxiliary social network, shown as a hexagon, and target factor nodes, representing each user in the target online social network, shown as a rhombus. Each factor node is connected to the variable nodes representing its potential matches. For example, F1 is connected to all the variable node profile pairs that contain user 1 in the auxiliary social network. Here we introduce the messages between the variable nodes and the factor nodes to compute the marginal distribution using belief propagation. We denote the messages from the variable nodes to the factor nodes as mu, and the messages from the auxiliary factor node to the variable node as lambda, and from the target factor node to the variable node as beta. In our 2 example, we describe the message exchange between the variable node x14, denoted as I, the auxiliary factor node F1 denoted as K, and the target factor node F4 denoted as Z. Following the general rules of belief propagation, the variable node I generates its message to the auxiliary factor node K by multiplying all the messages it received from its neighbor, excluding K. Note that in our case, each variable node has only 2 neighbors, 1 auxiliary factor node and 1 target factor node. Thus, the message from the variable node I to the auxiliary factor node K is computed as shown in the equation. This computation is done at every variable node. The message from the variable node I to the target factor node Z is also constructed in a similar way. Next, factor nodes generate their messages. The message from the auxiliary factor node K to the variable node I is given by the first equation, where Z denotes the normalization factor. The second term denotes the similarity between user 1 in the auxiliary social network and user 4 in the target social network. And the last term denotes the multiplication of the function of the received messages at the auxiliary factor node K, except from the message received from the variable node I. The function of a message is computed as 1 minus the received message. The above computation must be performed for every neighbor of each auxiliary factor node. The messages from the target factor node Z to the variable node I is also computed in a similar way. The next iteration is performed in the same way as the 5th iteration that we showed. The iteration stops when the probability distribution of all the variable nodes converge. The marginal probability distribution of each variable node is computed by multiplying all its incoming messages. To obtain a one-to-one match for each user in the target online social network, we get the profile pair with the highest probability. Assuming that there are n users in the Oxford social network and m users in the target online social network, since we can consider every possible combination, every user pair, the running time is OMN, so it is linear with respect to the number of variable nodes, in other words, user pairs. To evaluate our proposed framework, we use 3 data sets: Google plus Twitter, Instagram Twitter, and Flickr social graph from Zafarani et al. To collect the coupled profiles for the first and the second data set, we exploit the fact that users explicitly provide their social link in Google Plus and about.me. For the first and the second data set, we extract username, location, gender, profile photo, free text, posts, and their respective times. For the third data set, we use the number of connections. From each data set, we select 3,000 profile pairs for generating the model. This pair consists of 1,500 coupled and 1,500 uncoupled profile pairs. For the test, we select 500 users from the Oxford social networks and 500 users from the target online social network, where 500 of them are coupled profiles and the rest are uncoupled. Note that none of these users are involved in the training data set. Hungarian algorithm and the proposed belief propagation-based algorithm provide a one-to-one match between all the users. However, we cannot expect that all anonymous users in the target online social network have profiles in the Oxford social network. Therefore, some of the provided matches are useless for us. Thus, we select a similarity threshold, a probability threshold for machine learning techniques for evaluation, and consider as true positive the pairs that are correctly matched by the algorithm and whose similarity probability is greater than the threshold. We also compute accuracy as the number of correctly matched coupled pairs identified by algorithm over the total number of coupled pairs. For precision and recall, we compute them with respect to the similarity probability threshold. In this figure, we show the comparison of the proposed belief propagation-based model generation to the machine learning techniques such as k-nearest neighbor, decision tree, random forest, and support vector machine, and to the Hungarian algorithm. Our results show that the proposed scheme provides comparable precision and recall compared to the state-of-the-art Hungarian algorithm, and it significantly outperforms machine learning-based algorithm. At the same time, the complexity of the proposed algorithm scales linearly with the number of user pairs, while Hungarian algorithm suffers from cubic complexity. We also studied the effect of the online social network size to precision and recall of the proposed algorithm. In the figure in the right, we show the precision and recall values of the belief propagation-based algorithm where the number of users in the Oxford social network increases from 100 to thousands in step of 100, while the number of users in the target online social network is fixed to 100. For each online social network size, we report the precision recall values at which the precision recall curves intersect. We observe that the precision recall values of the proposed algorithm only slightly decrease with the increase of the auxiliary online social network size, which shows the scalability of our proposed algorithm. We achieve similar results for the other 2 data sets. We also study the limitations and properties of the proposed belief propagation-based model generation algorithm. We particularly analyze if the proposed algorithm maintains any optimality in any sense. For this, we use the following definition: Epsilon accurate model generation. We declare a model generation algorithm as epsilon accurate if it can match at least epsilon% of the users accurately. Here, accuracy is the number of correctly matched coupled pairs by the proposed algorithm over the total number of coupled pairs. Thus, for a fixed epsilon, we study the condition for an epsilon accurate algorithm to understand the limits of profile matching in online social networks. To have an epsilon accurate algorithm with a high epsilon value, we require the belief propagation-based algorithm to iteratively increase the accuracy until it converges. This brings us to the following sufficient condition. Accuracy of the model generation algorithm increases with each successive iteration until convergence if for all coupled profiles I and j, the probability of the pair I and j being coupled at the second iteration is greater than the probability of the pair I and j being coupled at the first iteration. Depending on the fraction of the coupled profile pairs that meet the sufficient condition, epsilon accuracy of the proposed algorithm can be obtained. There are many parameters to consider to analyze the epsilon accuracy of the proposed algorithm, such as the average degree of the factor nodes, the total similarity of each user in the target online social network with the ones in the auxiliary social network, the number of users in the target and auxiliary social network, and so on. We experimentally analyzed and showed the epsilon accuracy of the proposed algorithm considering such parameters. For the studied parameters, we observed that at least 97% of the coupled profiles that can be correctly matched by the belief propagation-based algorithm satisfied the sufficient condition. Here we studied the epsilon accuracy with respect to the number of users in the auxiliary social network. We observed that epsilon value is inversely proportional to the number of users in the auxiliary social network. The proposed algorithm achieves an epsilon of 94 when the number of users in the auxiliary social network is 100, and an epsilon of 84 when the number of users in the auxiliary social network is 1000, while the number of users in the target social network is fixed as 100. This decrease in accuracy can be considered as low, considering that the number of possible matches increased 10 times, since we consider every possible combination between the users. To study the impact of user pair similarity, for each user in the target online social network, we compute the variance of the similarity values between that user and all users in the auxiliary social network. Then we compute the accuracy of the proposed belief propagation-based algorithm on users with varying variance value. For evaluation, we use the first and the second data sets. Our results show that the epsilon accuracy of the proposed algorithm is higher for users with higher variance, as shown in the figures. These results show that the vulnerability of the users in an online social network can be identified by analyzing particular characteristics of the online social networks. The complexity of the belief propagation-based algorithm is linear with respect to the number of variable nodes. In the proposed belief propagation-based algorithm, we generate a variable node for all potential matches between the target and auxiliary online social networks. Assuming that there are n users in both target and auxiliary online social network, this results in n square variable nodes. To analyze the effect of number of variable nodes on the performance, we experimentally try to change the graphic structure and limit the number of variable nodes for each user in the target online social network. We heuristically decrease the average degree of the factor nodes from n to square root n and log n, by only leaving the variable nodes user pairs with the highest similarity value. For evaluation, we use all the three data sets. We pick 500 users from the auxiliary social network and 500 users from the target social network, where there are 500 coupled profiles. In the table, we show the results with varying numbers of variable nodes. For instance, for the first data set, Google plus Twitter, we obtain an accuracy of 67.4% when all the potential matches are considered. In other words, with n square user pairs, and an accuracy of 96% when we use only log n variable nodes for each user. These results are important since they show that while reducing the complexity of the proposed belief propagation-based algorithm, we can further improve its accuracy. To conclude, we have proposed a novel message passing framework to model the profile matching risk in online social networks. We have shown via simulation that the proposed framework provides comparable accuracy, precision, and recall compared to the state of the art, while it is significantly more efficient in terms of its computational complexity. We have also shown that by controlling the structure of the proposed belief propagation algorithm, we can further decrease the complexity of the algorithm while increasing its accuracy. We believe that the proposed framework would be instrumental for online social networks to educate their users about the consequences of their online sharing. As a future work, we aim to provide real-time privacy risk quantification in online social networks, propose possible countermeasures to mitigate this threat, and consider profile matching across multiple online social networks. Thank you for your attention.